In this segment, we're going to talk about the Fibonacci numbers, a famous sequence of numbers invented by an Italian mathematician. We're not doing this simply because they're fun, which they are, but also because it's going to teach us a little bit more about tuples and how we can use those in making function definitions. Just to remind you, in case you've not seen the Fibonacci numbers before, the way they work is that the sequence that start 0 and 1, and then you get the next number in the sequence by adding the two predecessors together. So 0 and 1 make 1, 1 and 1 make 2, 1 and 2 make 3, 2 and 3 make 5, 3 and 5 make 8, and so on. In general, if you've got two successive numbers u and v, the next number is u plus v. So how can we write that as a recursive definition? It turns out that it's pretty straightforward. We've got the function fib that goes from integer to integer. We define fib of 0, the first Fibonacci number to be 0, fib of 1 to be 1, and then for any other n, we get fib of n by adding together the two previous numbers. That's fib of n minus 2 and fib of n minus 1. And this is a variant of primitive recursion. So the value at n doesn't just depend on the value at n minus 1, it depends also on the value at n minus 2. But what we can see there is it still is a definition that will always give an answer, because if you start with a positive n, then the recursive calls to fib are to smaller values of n. So you will finish up computing, getting down to 0 and 1, where the definition bottoms out. But it's a very inefficient definition. Can you think why? Take a few seconds to speculate why it might be inefficient before we move on. Take a look at what calculating fib n requires us to do. It says we have to work out fib n minus 2 plus fib n minus 1. And that in turn requires us to do these two calculations you see below. But crucially, what you see here is that we have to calculate fib n minus 2 twice. So we'll do a whole lot of repeated computation. And each of those n minus 2's will have us calculating fib n minus 4 twice. So it turns into an exponential computation. For each 2 we subtract, we double the number of times that we compute that fib. And so you can see that's going to make it tremendously inefficient. And we can see that by dipping into VS Code and executing it. Let's do that now. On the left you see the definition of fib, and let's work out fib, say, of 20. Well, that's quite fast. What about fib of 30? That's a bit slower. What about fib of 35? Well, we're going to have to wait quite a long time for that answer to come. It should come along relatively quickly now, I hope. But if we were to ask for fib of 40, we would have to wait a tremendously long time for that. So what I can do, in fact, is press Control-C, and that interrupts computation. And that's a general way of interrupting computation in Haskell. Let's go back to the presentation now. Here we see a different approach to calculating fib. And what we do here is we do something rather different. It's just a little modification, if you like, of the thing we did before. But instead of returning just one Fibonacci number, we return two adjacent Fibonacci numbers. So fib p, fib pair, applied to 0 gives us 0 and 1. And then when we apply fib p to n, we have the previous pair. Now, if the previous pair are the numbers u and v, the answer for n will be v and u plus v. So we directly have the two numbers we need in order to calculate the next Fibonacci value. And what I've done here is I've written that definition in Haskell. You can see I've said precisely that. And what we do here inside the where clause in the definition of fib p of n, we match the result of fib p on n minus 1 against the pair uv, because we know that fib p is giving us a pair, so we call the first part u, the second part v, and then we know that fib p of n is v paired with u plus v. So you can see I had in the top line I've got, as it were, the informal formula, whereas in the code you see that rendered in Haskell. And let's see now how that behaves in computation. Here we are in VS Code. I'll just scroll down here and we can see we've got the definition of fib p here. Let's do fib p 20 and 30 and 40 and 400 and 4000. You can see that the results are coming very quickly because it's a linear algorithm. And we've got that simply by this trick of returning a pair of things, not just the previous value, but the value before that, or the two adjacent Fibonacci numbers. And that allows us to very, very efficiently do that calculation of Fibonacci. So this definition, where we return pairs rather than single numbers, is very efficient. And you can see we've used this, we've used the where clause here, this local definition, to extract the first and second half of fib p applied to n minus 1.